The other one. The pendulum won't take. Shut them off. Hey! 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 Hey!
This is a good ship royalist, a modern sailing training ship built along the lines of a brig with a traditional square rig on its two masts. She doesn't have much of a problem of finding her way across the world's oceans because she's fitted with modern navigational equipment. There are radar, direction finders, radio, modern compasses and accurate maps. In the Middle Ages, poor maps and the inability to find longitude at sea led many a ship to a watery grave. Until the 18th century, finding a position at sea was quite a problem. If all you wanted to do was to sail up and down the coast, then providing you would recognize familiar landmarks, you knew where you were. The moment you sailed over the horizon, then all you could see was sky, sea, and yet more sea. And one bit of this looked much like another. Under these circumstances, the mariner turned to the heavens for help. By fortunate coincidence, there is a star almost exactly above the North Pole. This is Polaris, or the North Star. Because of this fixed relationship between the star and the Earth, it is possible anywhere in the Northern Hemisphere, by measuring the angle between the star and the horizontal, to determine one's latitude, and therefore one's position between the pole and the equator. And there's a similar star which one could use in the Southern Hemisphere. However, to improve upon this, one really required a knowledge of the longitude as well. That is one's position in an east-westerly direction. Fortunately, the Earth is a natural clock, which turns once around its own axis in 24 hours, or to put it another way, turns to 15 degrees of longitude in 1 hour. If therefore we were to define noon as a time when the sun was directly overhead on the reference meridian, it would be directly overhead at different times in relation to the time kept here at all other points on the Earth's surface. Now in 1530, Gemma Frisi suggested that one could actually take a clock and set it correctly at the meridian, and then take it with one on one's journeys. Then one could always refer back to the standard time, and it should be a simple thing to calculate one's longitude. Now, to achieve the construction of a clock, which could go to sea, which would keep accurate time over all this period, proved to be a very difficult thing indeed to achieve. It was in 15th century Tuscany that a man was born who greatly affected the scientific world of that time and who played an early part in the longitude problem, Galileo Galilei. Although his father ran a music school, Galileo was much more interested in science. Living in Pisa, he often used the famous Leaning Tower for his experiments. But he first exercised his scientific mind in here, Il Duomo, the magnificent cathedral next door. Legend has it that as a 19-year-old medical student, he was fascinated by the way the great cathedral lamp swung back and forth. He noticed that it didn't seem to matter how big the arcs of the swings were, they all took the same amount of time to complete. Not having an accurate clock, he used his pulse to time the oscillation. What Galileo had discovered was a key to accurate mechanical timekeeping. Let's have a look at this. I'm going to start these two pendulums off with very different arcs, and yet we can see that they pass the center line at the same time. Even though the arc of the swing is much bigger on the front one, the period is the same. Now let me start all three pendulums at the same time, like that. Now they beat beautifully in synchrony, yet I haven't told you the bobs are made out of brass, lead and iron. They're therefore very different weights. So we have another discovery here that the period of the pendulum is independent of the mass at the end of it. So we only have one remaining variable, which is its length. When I shorten the front pendulum, we can see immediately that it beats faster. So in the pendulum, we have a possible basis for an accurate clock And indeed, towards the end of his life, Galileo concerned himself with the design of such a clock. However, in the meantime, actually in this villa, Galileo was considering other methods which would not require a transportable timekeeper. What he was really looking for was a clock in the sky, visible simultaneously from different locations on the Earth's surface. He suggested the use of the transit of 4 of the moons of Jupiter across the face of the planet, and indeed constructed a set of tables based on a reference meridian running through the Canary Islands, from which it was possible to calculate the longitude from anywhere where the moons were visible. Unfortunately, the method failed at sea because of the difficulty of using a fairly powerful telescope from the heaving deck of a ship. In 1675, the search for a method of finding longitude at sea switched to England and a piece of spare ground in the Royal Park south of the River Thames at Greenwich. Charles II appointed John Flamsteed, a vicar and member of the Royal Court, as the first astronomer royal. Flamsteed moved quickly and, acting on advice from Sir Christopher Wren, established the first Royal Observatory. Christopher Wren designed the observatory and used largely second-hand materials derived partly from a palace which used to stand here and partly from the old fort at Tilbury. Charles II was deeply worried about the heavy losses of valuable ships. He was anxious that Flamsteed should find a solution to the longitude problem. Flamsteed looked for a more practical astronomical method. The solution which was being put into practice is called the lunar distance method. The principle is as follows. The moon appears to move slowly against a fixed background of stars. If at Greenwich, therefore, a table is constructed which relates time to the position of the moon in relation to certain prominent fixed stars, then anybody, anywhere in the world who can see the moon has access to Greenwich time. If in addition to that, they know local time, which you can also derive from the movement of the stars, then they have all the information which allows them to calculate longitude. Now, it took 60 years of the combined labors of John Flamsteed and Edmund Halley to accumulate the required data. Flamsteed spent 40 years charting the movement of the stars, and Halley another 20 years recording the movement of the moon. It was a very difficult task, which was very nearly beyond the technology of the time. For instance, Halley spent nearly 2 years engraving the scale of this quadrant, which he used for his measurements. In the meantime, dozens of ships, valuable cargoes, and thousands of lives were lost, merely because the ships lost their way. The worst was Admiral Sir Cloudesley Shovel's in 1707. He was returning with his fleet from Gibraltar and thought that he'd reached safe water. Then, in the evening of September the 29th, 4 ships struck rocks just off the Scilly Islands. 2,000 men were lost, including the admiral. Because the measurements took such a long time, not surprisingly, the government of the day was pressured by merchant and ship owners to do something about the seemingly impossible longitude problem. After taking advice from Sir Isaac Newton, in 1714, a bill was presented to the Commons and shortly afterwards ratified by the Lords, entitled "A Bill for Providing a Public Reward for such person or persons as shall discover longitude at sea." A board of longitude was set up, which offered huge prizes, up to £20,000, for finding longitude to half a degree of accuracy, roughly 30 nautical miles. Sir Isaac Newton favored 3 methods: the Jupiter's moons method, the lunar distance method, and a portable clock. He said he didn't really consider a watch at sea a practical proposition because of the motion of the ship, the variation of heat and cold, and wet and dry, and the difference of gravity at different latitudes. A young carpenter's son from Yorkshire was convinced that the great Isaac Newton was wrong, however. In 1728, John Harrison, then 35 years old, came to London, bringing with him the designs of the world's first marine chronometer. It weighed 72 pounds, incorporated a host of new inventions and designs, which largely solved the problems which Sir Isaac Newton had identified. Harrison replaced the troublesome pendulum by a pair of oscillating dumbbells controlled by springs. The merit of having two balances work in opposition to one another is that they cancel out any effect which a rolling of a ship might have had on a single balance. He also invented a system of temperature compensation. One of the problems is that changes in temperature change not only the length of the balances, but also the strength of the springs. His invention, which he called the gridiron, deliberately makes use of the differential expansion of two different metals to produce a large mechanical movement, which he then used to compensate for the temperature effect on the balances. Let me show you how it worked. This is a sandwich of brass and iron. The brass expands more than the steel for a given rise in temperature. So if I heat it, the gas flame here, the relatively small movement of the two pieces of metal becoming longer is amplified into this large movement at the tip of the strip. Now Harrison used this principle to effectively adjust the length of these springs to compensate the balance. Now, every mechanical clock has to have a device called an escapement. Its main function is to meter out the energy stored in the spring in such a way as to drive the clock. But it has a secondary function, and that is to deliver little mechanical pushes to the balance system in order to keep it going. And to do this in such a way as not to disturb the very accurate timekeeping qualities of the balance. Now, Harrison invented a new kind of escapement, which was later called the grasshopper escapement. The clock took 6 years to build, and in the spring of 1736, Harrison set sail from Portsmouth to test it at sea. His destination was Lisbon. On the return journey, Harrison proved the captain to be out by almost 90 miles, demonstrating the superiority of his clock over the then conventional navigation. With the government now providing the funds, Harrison built another clock, the H2. It included even more new ideas, one of which was this remontoir or rewinder. It is a secondary spring that isolates the jerky unwinding of the main spring from the mechanism of the clock. It was a bigger and better clock in every respect. It weighed 102 pounds, and the balance dumbbells themselves weighed 6.5 pounds. It's interesting to note at that time it was thought that an accurate clock also had to be a big clock. This clock took 2.5 years to build. It was actually never tested, probably because it became available at the time of the war with Spain, and because an accurate clock was of the nature of a secret weapon, because a navy which actually knew where it was would have a tremendous advantage. It was thought to be too valuable a property to risk being captured. H3 took 19 years to make. It can really be regarded as a crystallization of Harrison's life, because he lavished every care and attention on it. It differs mainly from H2 by a replacement of the oscillating dumbbell balance weights by circular balance wheels. With this clock, he intended to win the £20,000 prize. Just before he was ready to submit it to the board of longitude, he suggested that he should also make a deck watch. His suggestion was accepted, and he made this most beautiful deck watch, which he called H4. Now, he didn't intend it to have any particular long-term accuracy, because it was to be used to transport time from H3, which was going to be kept in the bows of the ship at the point of minimum motion, to the deck where the actual astronomical observations were going to be made. Much to his surprise, H4 actually performed better than H3. As the reason for this was probably, so it wasn't appreciated at the time, that the balance wheel of H4, and we can see the balance wheel oscillating in the copy here, oscillated very much faster and was very much lighter, of course, than the ponderous balance wheel of H3. Now, this probably gave it a greater immunity from the motion of the ship. Harrison decided to use H4 as a sole entry for the prize. His son set sail for the first trial on the 18th of November 1761. Their course took them to Jamaica via Madeira. After 9 days out of sight of land, there was a 15-degree difference in longitude, estimated by the captain and calculated using H4. H4 was right, and by the following day they sighted Madeira, much to the relief of the crew, because they'd run out of beer. On his return from Jamaica, the watch was found to have performed well within the rules, and Harrison should have won the prize. The problem was that the watch cost £400, which was actually more than the cost of the ship which had carried it. And so far, there was only one watch. In the meantime, two other things had happened. The astronomer royal, Neville Maskelyne, had collected all the data on the stars and the moon in a set of tables called the Nautical Almanac, that I've got here. And secondly, Ramsden had invented this dividing engine, which made it possible to produce precision measuring instruments, such as this octant, with its finely engraved scale, and later on the sextant, relatively cheaply. It was ever possible, by use of the Nautical Almanac and one of these measuring instruments, to determine longitude at sea, but with some considerable difficulty. Maskelyne naturally thought that he should win the prize, and regarded Harrison and his clocks with some trifling hostility. However, the watch was still regarded to be better and easier to use, so it was decided to run a second trial, this time with Maskelyne on board. The watch behaved even better, with an error of less than 1/10 of a second per day. But the board still wouldn't pay up, because they wanted to be assured that more watches could be made. So Harrison, by now an old man and nearly blind, set to make a second watch, which actually represented his 5th attempt to meet the rules of the contest. The Board of Longitude also made drawings of its mechanism and asked another clockmaker, Larkham Kendall, to make a copy. This was tested by Captain Cook on a second voyage to Antarctica and the South Seas between 1772 and 1775. Using the watch, Cook was able to map his progress very accurately, had nothing but praise for it, and insisted on taking it on a third voyage. During these 3 years, King George III had come to Harrison's aid. He thought he had been badly wronged, and finally the government, out of embarrassment, paid the prize money. Harrison had spent 50 years of his life in making the first marine chronometers. Now that there were accurate means of keeping time, ways had to be found of synchronizing the timekeepers. This time signal was installed in 1833 to signal the occurrence of 1 o'clock to all the ships in the Pool of London. Although the mariners were more than happy to use Greenwich time, the rest of the country wasn't. Each town kept its own time, measured from noon. But when it was noon at Greenwich, it was only 11:46 in Torquay. When the railway started, they needed a common time, so many clocks had 2-minute hands, one showing local time, the other railway time or Greenwich time. People were confused, a situation that was not helped by the post office having its own time, kept at St. Paul's. Thankfully, eventually everybody agreed to use Greenwich time, and time balls cropped up all over the place and were linked by telegraph to Greenwich. This beauty was on the old Kent Road. But there also had to be a reference line, a meridian, from which longitude was to be measured. France, along with the other major powers of the time, insisted on having their own meridian. This one passes to Paris. But in the October of 1884, at an international conference held in Washington, the Greenwich meridian was made the prime meridian, zero longitude of the world. The meridian passes right through the center of this instrument, which was built by Professor Airy to correct the timekeeping of man-made clocks by observing the regular movement of the stars. The observer watches the passage of the chosen star across wires mounted in his eyepiece. The moment that occurs, he presses this button. Pressing this button makes a mark on a drum, on which a master clock also makes marks at 2-second intervals. Subsequently, it is possible, by comparing these two tracks of marks, to work out a correction for the master clock. The other clocks in the observatory are then reset until it's time for the next clock star to pass overhead. Today, we move around at very high speeds. A tiny navigational error made by these pilots would end in disaster. Accuracy of measurement is becoming increasingly important. Airy's transit circle has been replaced by this, the laser ranger at Hurstminster Castle in Sussex, the home of the new Royal Observatory. It sends out pulses of laser light, which are reflected back by a special satellite. The position of zero longitude is then calculated to an accuracy of a few centimeters. With it came a new breed of clock. Here at the National Physical Laboratory in Teddington, we have the granddaddy of all atomic clocks, which helps to regulate clocks all over the world. It doesn't use a pendulum or a balance wheel or even a quartz crystal, but the oscillations of cesium atoms in a beam of cesium vapor. What happens is that we create the beam of cesium vapor at this end of the machine. The beam passes through the center section of the machine. Radio frequency energy is injected down this waveguide to excite the oscillations of the cesium atoms. The oscillations are detected at that end and then converted electronically into a digital display of time. This clock is so accurate that it wouldn't gain or lose more than a second in 300,000 years. In fact, it is so accurate, it has allowed us to demonstrate that the constancy of rotation of the mother clock, the Earth, isn't as great as had been thought, and in fact isn't good enough for modern navigation. If a navigator wants to establish his position on the Earth's surface to an accuracy of a few meters, or sets off on a journey of space exploration, then he still has to take a clock, just like the early explorers. But this time, it has to be a clock which is at least 1 million times more accurate than Harrison's chronometer.